In this video, I would like to practice solving trig equations of a slightly more complicated nature. In particular, we're going to focus on solving trig equations where the input of the trig equation is not just x, is not just t, but maybe the variable is inside cosine with some other stuff. For example, maybe you have 3 times x inside of cosine instead of just x. The second thing that I'm going to look at today are trig equations where maybe there is more than one trig function in the equation. Maybe you have both a sine and a cosine. Maybe you have a cosine squared, something like that. In that case, we're going to solve those kinds of equations using factoring. So in this exercise, let's demonstrate what needs to be done if you're trying to solve a trig equation where the input of cosine is not just the variable. In this case, the input of cosine is 3 times the given variable. I'm going to start this problem in much the same way that I did the exercises from yesterday. The first thing that I'm going to do is I'm going to use arc cosine, and I'm going to use the unit circle to find all the angles at which cosine outputs -1/6. The big difference between this question and the one before is that the angles that I find are going to be equal not to the final answer. The angles are going to be equal to the input of cosine. The angles in this case are going to be equal to 3 times x. And therefore, to actually find the values of x, I'm going to have to divide the angles by 3. Okay, so to begin with, let's find one angle at which cosine outputs -1/6. This angle can be found using arc cosine. So let's plug this into a calculator and see what we get. This is not one of the values on the unit circle. -1/6 does not appear in that reference image as any of the x coordinates in that picture. So let's use a calculator to find this value. And I get a radians value of 1.403. Okay, now this is one angle where cosine outputs -1/6. So now let's go ahead and find all the other angles. So using the unit circle as a guide, I'm looking for locations where the x-coordinate is equal to -1/6, and the value that arc cosine has just provided for me is the one that's pointing into quadrant number 2. Remember, arc cosine can only ever produce angles which are between 0 and pi. So because the angles produced by arc cosine are between 0 and pi, those angles can never reach into quadrants 3 or 4. They can only reach into quadrants 1 or 2. So here's the angle 1.403. What angle will get me to this other location on the unit circle with the same x-coordinate? I can just go the opposite, -1.403, to turn clockwise instead of counterclockwise. And so that is another angle where cosine will achieve the same output. So the angles at which cosine outputs -1/3 are given by 1.403, or any coterminal angle to that, or -1.403, or any angle coterminal to that. However, these are not the values of x. These are the values of the angles that are being plugged into cosine, and the angles being plugged into cosine are equivalent to 3 times x. So what have I just found? I've just found that 3 times x, the input of cosine, can be equal to either positive 1.403 plus 2 pi k, or 3x can be equal to negative 1.403 plus 2 pi k. So now, to find the actual values of x, the next thing that I'm going to do is divide everything through by 3. And dividing the 2 pi k by 3, I get 2 pi k over 3. And likewise, the other inputs can be found from the other branch, negative 0.468 plus 2 pi over 3. This can be obtained by dividing by 3. These are the numbers which can be substituted for x that will make the given equation true. If x is equal to any of the numbers described here, then 3x will be equal to an angle at which cosine outputs negative 1 over 6. So that will make the given equation true. Now, as a warning, when you're working on problems where you're trying to solve a trig equation and the input of your trig function is not just x, you have to be careful to make sure that you're adding the 2 pi k at the right time. You cannot add 2 pi k at the very end of the problem. You have to add 2 pi k when you're writing down all the angles. You see, in the previous exercise, if I had written down the plus 2 pi k at the very final step, then I would have gotten the wrong answer. In the true final answer, the 2 pi k also got divided by 3. So in the end, we actually ended up with a 2 pi over 3 times k, a 2 pi over 3 times k, not a 2 pi k, not in the final answer. So make sure that you're adding 2 pi k when you're describing the angles, right here when you're describing all the angles coterminal to the ones that you found. Let's reinforce this with another example. Suppose that I'm trying to solve sine of pi times x equals 1/3. So in this case, the thing that's being plugged into sine is the quantity pi x. So the quantity pi x is the thing that's representing the angles. So bearing that in mind, let's start by figuring out the angles that make sine produce an output of 1/3, and then from that, let's determine the value of x. Okay, so the first thing that I'm going to do is find one angle using arcsine. So I'm going to determine the value of arcsine of 1/3 using the calculator. This is equal to 0.340 radians. Now let's use this answer together with the unit circle to find all the other angles at which sine outputs this same value. I'll indicate the height of y equals 1/3, maybe right around here. And the value that was output by arcsine is the angle that is between negative 90 degrees and positive 90 degrees. So it cannot be pointing to this location in quadrant 2, it must be pointing to this location in quadrant 1. But for sine, in order to get this location on the left side of the circle, I need to go forward by half a rotation, forward by pi units, and then backtrack by 0.340 radians. So pi minus 0.340, which is approximately equal to, okay, so let me show you now the wrong answer. This is what you don't want to do. What you don't want to do is say, okay, so I've just found these two angles on the unit circle where sine outputs 1/3. And the angles on the unit circle are equal to the input of sine, which in this particular problem is pi times x. What you don't want to do is say pi times x, therefore, must be equal to either the angle 0.340 or the angle 2.801. What you don't want to do is take this and then divide by pi to say that x is equal to either 0.340 divided by pi, or x is equal to 2.801 divided by pi. And what you don't want to do is say, then add 2 pi k. The issue here is that you've added the 2 pi k at the wrong time. This individual has added the 2 pi k as an afterthought at the very end of the problem, and this isn't going to work. These values of x are not actually the solutions to the given equation. You need to add the 2 pi k when you're describing the angles that cause sine to produce a value of 1/3. So you need to add the 2 pi k back when you're describing the angles. The angles can be 0.340 or any other angle coterminal to that. The angles can be 2.801 or any angle coterminal to that. These, therefore, are the possible values of the input, pi x, What, therefore, are the possible values of x? To get the values of x, we need to divide everything out by pi, including the 2 pi k. So that changes in the final answer. That changes the 2 pi k to what is now just 2k, because the pi has been divided out. So be careful. You want to make sure that you're adding the plus 2 pi k when you are finishing describing all of the angles that make sine or cosine do whatever is needed. Then, potentially, that 2 pi k is going to get changed when you isolate the actual x that you're solving for. For part 2 of the talk about slightly more complicated trig equations, let's look at problems that potentially have more than one trig function in them. For example, someone asks me to solve sine of x times cosine of x equals 0. Now the zero product property is a rule from algebra that helps you to solve equations like this one. It says that if you have two quantities which are multiplied together, and then you know the result is supposed to be 0, then you can break this equation down into a equals 0, separate from b equals 0. So you can split a complicated equation into two simpler equations. But this only works in the case that you have a product of two things specifically equaling 0. This is a very unique property of two quantities being multiplied together to equal 0. Now, how does that apply in an exercise like the one that's given to us? This applies because we can solve separately the equations sine of x is equal to 0 or cosine of x is equal to 0. Now, the nice thing about both of these two equations is that the output that we're looking for from sine and from cosine is 0, which is a value that is very easy to see on any reference image of the unit circle. If we're looking for angles at which cosine outputs 0, we're looking for angles that will point us toward either the very top or the very bottom of the unit circle. And if we're looking for locations where sine is expected to output a 0, we're looking for locations either at the far left or the far right side of the unit circle. So let's write down all of the angles that would position us at one of these four locations. For example, if I wanted to be on the far right side, I could use an angle of 0 or any angle coterminal to that. Here at the top, I could use an angle of 2 pi or any angle coterminal to that. Far left would be pi or angle coterminal to that. And at the bottom, I could use 3 pi over 2 or any angle coterminal to that. So these would be the angles which would satisfy the given equation. And since the input of both sine and cosine is just equal to x, the x values and the angles in this equation would be exactly the same. So this would be my solution to this equation. For a similar example, let's consider a problem like we have down here, where we would have 2 times cosine squared plus 3 times cosine plus 1 is equal to 0. Now, in terms of using the zero product property, we do have the 0 on the far right side. That's nice. But what we're lacking at the moment is the product part of the zero product property, where I have something multiplied by something else equals 0. Because I'm lacking that product, what I'm going to try and do is factor the equation. And to demonstrate how I would factor the equation with cosines in it, let me show you how to factor the equation that just has a single letter, p, in the place of cosine. So 2p squared plus 3p plus 1 can be split apart. The 1 only splits as 1. The 2 can only be split as 2 and 1. So this is the factorized form of 2p squared plus 3p plus 1. And from this, I can use zero product property to say that either the 2p plus 1 is 0 or the p plus 1 is 0. So the p must be equal to -1/2 or -1. Now this is how we factored quadratic equations back in algebra. And we can apply exactly the same technique here in this equation, where instead of having a p squared, we have a cosine squared, and instead of having p, we have cosine. To factor this more complicated expression, we can, for simplicity's sake, just nickname the cosine by the simpler single letter p. That way we get the equation 2p squared plus 3p plus 1 equals 0, which we can factor using algebraic techniques. And by using zero product property, we can conclude that the values of p are equal to -1/2 or -1. And since p in this problem was just our nickname for cosine, we can conclude that cosine needs to output either -1/2 or cosine needs to output -1. Now these outputs, just like in the previous problem, are pretty convenient because they do show up on our unit circle reference image, and therefore we do not need to use our calculator and the inverse sine and the inverse cosine function on our calculator to help us to figure out the angles where these outputs are achieved. We can really just read them off the circle. For example, the circle tells us that cosine equals -1 on the far left side, where the angle is equal to pi, or any other angle coterminal to that. Cosine equals -1/2. Let's go back to the reference image just to check out where cosine equals -1/2. According to the circle, we get an output from cosine equal to -1/2 at the angles 2 pi over 3 and 5 pi over 3. And of course, any angle coterminal to either of those will also work. Now, in this problem, the input of cosine is just x, and therefore the x values are an exact match to the angles. So therefore, our final answer to this question is that if you want this equation to be true, you can plug in an x which is equal to pi, or any coterminal angle. It's equal to 2 pi over 3, or any coterminal angle, and also 5 pi over 3, or any coterminal angle, will work. This is the complete list of all solutions to the given problem. Let's conclude today's video with one final example. At first glance, this problem might seem fairly similar to the one before, because we have an equation that has a trig function squared plus a plane trig function plus a constant. And that was pretty similar to what we had in the previous example with 2 cos squared plus 3 cosine plus 1 equals 0. But the big difference between the equation in this exercise and the equation in this exercise is that there is a mismatch in this example between the actual trig functions in this equation. Whereas the previous exercise contained only cosines, this equation contains both cosine and sine. So this is going to create some issues because if we tried the same trick that we used before of using a nickname, p equals cosine, then I would be able to use this nickname to simplify the first term to 2p squared. But I would have to introduce a different letter for sine because sine is going to be a different number. So maybe q or something like that. And now, because this equation has 2 different letters in it, it's no longer possible to factor this using the techniques of algebra. So instead, we're going to use a trick to help us to transform this equation so that there's only one variety of trig function in it. And the trick that we're going to use is the Pythagorean theorem. Or I should say, specifically, the Pythagorean identity. Remember that the Pythagorean identity said that if you take cosine of something and square it, and take sine of the same something and square it, that the result is always equal to 1. Now suppose that I take this equation and rearrange it slightly to isolate cosine of x by subtracting sine of x from both sides. This identity says that if you're working with an equation that has a cosine squared in it, that cosine squared can be replaced by a 1 minus sine squared. And this is great because that will allow me to get an equation that has only sines and no cosines. I'm going to put this data into the equation to replace 2 times cosine squared with 2 times the quantity 1 minus sine squared. So this is equal to negative 2 sine squared x plus 3 sine x plus 2 from 2 times 1 plus 3. So now that we've turned this into an equation that has only a sine squared, a sine, and numbers, now let's try and use that trick of nicknaming sine of x by a simpler singular number. And after making that replacement, trying to algebraically factor this equation so that I can use zero product property. I will probably just use guessing and checking, and I think this will work, yes. Plus 5p minus 2p would be plus 3p. If you're rusty about how to factor slightly more complicated expressions, I'll post a video in the description about the AC method for factoring, which is a little longer but more reliable. So zero product property says that either negative 2p plus 5 could be 0, or p plus 1 could be 0, which means that p could be equal to 5 over 2, or p could be equal to negative 1. So now let's go back and remind ourselves that p was just a nickname for sine of x. And we're trying to find values of x that will make either one of these equations true. However, something is immediately a little bit suspicious about the first equation, and that's that we're asking sine to output a value which is larger than positive 1. This isn't possible because 2.5 is greater than any y-coordinate on the unit circle. So we're not going to get any solutions from this branch. The only solutions that we might possibly get would come from the branch sine of x is equal to negative 1. So let's have a look at the unit circle, because minus 1 is a commonplace unit circle value. Sine of x equals negative 1 only occurs at one location, at the very, very bottom of the unit circle. What angle would put me down at this location? The angle that would put me at that location, one such angle is negative pi over 2, and any coterminal angle would also work. There are no other locations on the unit circle with this y-coordinate, so there are no other angles which satisfy sine equals minus 1. Now in this case, the input of sine is equal to x only, and therefore the x is equal to the angles. And so my final answer to this problem would be that x could be equal to negative pi over 2 plus 2 pi k, where k has to be an integer, so we're working in full rotations. That concludes today's material. Today we talked about solving trig functions of a slightly more complicated flavor. The first complication that we introduced was the possibility that the quantity that was being plugged into your trig function was equal to something more complicated than just x. In all cases, the quantity that is the inside of sine, the quantity that is inside of cosine, is what is equal to the angles that you're looking for in the problem. You start by finding the angles at which sine or cosine outputs the desired value, and writing all of those down, including the 2 pi k. Then use the fact that the angles are equal to the input of sine, the angles are equal to the input of cosine, and then solve for x. The second complication that we studied, your trig equation has more than one trig function in it. In that case, the usual technique is to use zero product property. In some cases, you may be lucky and your equation may already be factored. In some other cases, you may need to factor yourself.